In this video, I'm going to prove the Lagrange mean value theorem and Cauchy mean value theorem using a not so common technique, that is to construct a kernel function. So when we observe this equation, this desired result, if we just observe what they have in common, right? Lagrange and Cauchy. So if we just divide f, the left hand side, onto here and divide a over b over there, we should have 1 over f prime of Cauchy over fa minus fb is equal to 1 over a minus b. And likewise, if we divide fa minus fb over here, f dash of zeta over fa minus fb is equal to g dash of Cauchy zeta over ga minus gb. So what they have in common is that on the left-hand side, they both have f dash of some number, right, over fa of minus fb. And the only difference is the right-hand side. So how can we construct a kernel function, right, that have some certain properties? So since it's a derivative, then what's its antiderivative? Right, let's say its antiderivative is x over a minus b plus some constant, right? And so what is its antiderivative? ga minus gb. Perhaps it's g of x, right? That's its antiderivative, plus some constant. Right. Could this be the so-called kernel function? So what's the value of c? Right. If we remember Rolle's theorem, we require fa equal fb. Right. If we let x equal to a, right, a plus c over a minus b. What if x equal to b, b plus c over a minus b? So it's almost impossible to let fa equal to fb. So in this case, we can just, let's just say, could c equal to perhaps minus b? C equal to minus b. So x minus b over a minus b. So in this case, if we plug a into here, we have 1. If we plug b into here, we have 0. Right? So they're not equal to each other, but it's already good enough. I'll explain why. So what if we let c equal to just minus gb, right, over ga minus gb. If we plug a into here, we have 1. If we plug b into here, we have 0. All right? It's already good enough for me. So can we perhaps construct a kernel function lambda of x, where lambda is continuous on closed interval ab, and also is differentiable over open interval, and also lambda of a is equal to 1 and lambda of b is equal to 0. Right, this is my kernel function. And And so this is my special case, special lambda, another special lambda, right? So overall lambda is my kernel function. So in this case, can I say that under this condition, can I say that, let's find out, there exists, C zeta, let's use eta, right? Eta, open interval, eta, right? Exists in the open interval so that f prime of eta over fa minus fb, I'll just multiply it over, is equal to, could it equal to fa minus fb quantity multiplied by lambda prime of eta, right? This is my claim. So under this condition, right, if I can just, right, can I show that f prime of eta minus fa minus fb quantity times lambda prime of eta is equal to 0. Right, can I show that? So in other words, can I, what's the antiderivative? Right? Can I construct a function called h of x, called f of x minus quantity fa minus fb quantity times lambda of x, right? Can I verify the value of h of a? What is h of a? F of a minus f of a minus fb times lambda a. Like I said, lambda of a is equal to 1. So that is equal to fa cancel out, minus minus fb, right? So what is h of b? That's f of b minus f of a minus f of b times lambda of b. Like I said, lambda of b is 0. So h of b is equal to f of b. So in other words, h of a equal to h of b. So is h of x continuous over closed interval ab? Yes. Is h of x differentiable over open interval ab? Yes. Right? F. So in other words, h of x satisfies the condition of Rolle's mean value theorem. Right? So in other words, there exists a lambda. There exists a lambda so that h prime of lambda is equal to 0, right? That is, this equation is equal to 0, right? So this is true, really true. So like I said, I've constructed such a kernel function satisfying the following conditions, and successfully I've proven my claim is really true. Then like I said, this is just the special value of lambda, right? Some appropriate function lambda. Then we can simply prove the Lagrange mean value theorem and the Cauchy mean value theorem. Like I said, for example, I can let lambda equal to a minus b under x minus b, right? Of course, lambda a is really 1, lambda b is really 0, right? So function is really continuous over ab, closed interval ab, and really differentiable over open interval ab. So really satisfied. So according to my claim, f of course, assume that f satisfies these conditions. So therefore f of lambda, f of perhaps Cauchy, f of Cauchy, f prime Cauchy is equal to fa minus fb times lambda prime of Cauchy. Lambda prime is what? Is 1 over a minus b, right? It has nothing to do with Cauchy anymore. So in other words, if I just multiply a minus b over, right, I should have this equation. So this Lagrange mean value theorem is really true. Now, if I just choose another lambda of x as ga minus gb under g of x minus g of b. Right? So lambda of a, is it equal to 1? Yes. Lambda of b, is it equal to 0? Yes. So assuming that g satisfies these conditions, so is lambda satisfied these conditions? Yes. So according to my claim, so there exists a eta, right? Maybe zeta different. So maybe different, right? So that f of maybe zeta, f prime zeta is equal to fa minus fb times lambda prime. What's lambda prime? G of a minus gb, g prime of zeta. GB is gone, right? Constant. So this is true. If I just divide g prime zeta, right, over here and keep GA minus GB, right, then I have Cauchy mean value theorem, right? According to the kernel function. So like I said, I've constructed the kernel function motivated by observing what those two equations have in common. I just divide fa minus f over here. Right, what they have in common is f prime over fa minus fb. Then that's how I constructed the kernel function. Maybe it's not that natural compared with the other proof, like for example, this is I still think it's relatively natural. It's not that bad. AB, FA, FB. Right? This is the graph of F. And then we just construct a line. straight line segment. Right. Then we can easily work out the function of the straight line. Right. Say perhaps it's L of x. Right. L of x. Then we construct a new function. H of x is equal to f of x minus L of x. Right? If we plug a into this function, right, obviously those two graphs of the functions meet exactly at this point where they just equal to each other exactly, so they just cancel out to be 0. And so same thing happens at the edge of B, right? So that h of a is equal to h of b equal to 0. So h of x satisfies the condition of Rolle's mean value theorem. So perhaps this way is more natural compared with the kernel function, but this is not so bad, not too bad. Right. So when we construct the Cauchy mean value theorem, right, Cauchy. So f, maybe we can use the t, right? ft gt, right? Parametric function, right? ft. Right? Perhaps this is a curve. Curve. Right? X is ft, y is gt. Right. T is the parameter. Right. Maybe this is the graph. And maybe we just connect those 2 points. Right. With this point, t is equal to a. Maybe this point, t is equal to a. This point, t is equal to b. Right? So the f prime of g prime, maybe it represents the gradient of this line segment. Right? So intuitively, it makes perfect sense. Right? Right? The gradient of the line segment must be equal to some tangent line's gradient, right? Maybe at this point, maybe I have a tangent line whose gradient is equal to exactly the gradient of this line segment. Right? Intuitively, it makes perfect sense. And still, we following the same technique. We construct a new function. Right? That is the difference between the function of this curve and the function of this line segment. Then the new function has exactly the same value at both edges.